System design sounds intimidating, like some guarded secret only senior engineers with a decade of experience get to touch. But at its core, it's the architectural logic required to keep a piece of software alive when millions of people try to use it at the exact same time. Writing functional code on a laptop is a starting point. However, deciding where data lives, how fast it loads, and how to direct a massive flood of traffic requires a completely different mindset. Code builds the application, but the system design is what keeps it running when it hits the real world. Let's say you build a straightforward Notes app. You put it on a single server. Right now, you are the only person using it, and it works flawlessly. Then, overnight, a popular influencer shares a link to your app. Suddenly, 1 million people try to log in at the exact same moment. The app slows to an absolute crawl. Within minutes, the server overloads and crashes completely, taking everyone's unsaved notes down with it. The code functioned as intended, but a single machine can only process so many requests per second before its memory maxes out. To survive explosive overnight growth, you have to tear down that basic setup and replace it with structural defensive pillars. When traffic hits, a single server node glows under an overwhelming wave of data. To fix this, we introduce the first pillar: scalability. Upgrading one machine's power hits a physical limit. Instead, the node duplicates, spreading horizontally into a wide array of identical servers. Adding more machines to share the load is the mandatory standard for any massive application today. But 50 servers won't help if all users still connect to the first machine. This requires our second pillar, a load balancer. Think of it as a digital traffic cop, intercepting every user and routing them to the least busy server. Raw computing power requires a centralized mechanism to intelligently distribute the burden. So servers handle the traffic, but where are those millions of notes actually kept? Looking at this diagram, we see the third core pillar forming below the servers. This heavily reinforced vault is your database, the secure, long-term home for all application data. You might choose a highly structured SQL database for a bank, or a flexible NoSQL database for a constantly updating social media feed. But there's a massive bottleneck. Forcing servers to dig into a heavy database for every single request is far too slow for modern expectations. We solve this speed problem with our fourth pillar, a cache, a lightning-fast layer inserted above the database. It's how Instagram loads instantly. Popular data is kept here, so requests bounce off the service layer back to you, bypassing the slow database completely. True system efficiency relies on positioning high-demand data for instant access while maintaining the security of the long-term vault. Let's look at exactly how these four pillars work together to handle a single request in a bulletproof architecture. In this diagram, watch the exact path of a user opening the app. Their request flows through the load balancer, which smoothly routes it to a single available server. The server immediately asks the cache for the data. If the note is already saved there, the packet turns green and rockets back up to the user. The trip is over. But if the note isn't in the cache, the server pushes past it, digs into the database vault, retrieves the data block, and sends it all the way back up the chain. This entire multi-layer journey, routing through traffic cops, checking short-term memory, and digging into vaults, happens invisibly in a matter of milliseconds. System design applies a logical framework to complex infrastructure problems. It provides a structure capable of handling massive crowds, managing their data without losing it, and keeping the entire experience perfectly stable. If this breakdown clicked for you, drop the word system in the comments below. We'll be diving much deeper into each of these pillars in an upcoming full series. Understanding these four pillars provides the foundation needed to design software that can handle the scale of the modern internet.